So this is, uh-oh, the pen's not working. Come on, pen. There you go. This is lesson 4.3. And I see a couple of you already rocked through this. Congratulations. I call it finding time. And the big theme is about an idea in math called logarithms, which in addition to being a cool looking and sounding word, actually is synonymous with the word exponent. So a logarithm is an exponent. So I'm just going to give a couple of examples of how that verbiage works, a couple of examples of how the math part of it works, and then we'll go and work on some problems together in the lesson. So literally, logarithm means exponent. So just some examples of exponents, and I'm going to stick with 10 as the base for a minute. 10 to the first power is just right a 10. Right, not much happens there. 10 to the second power means 10 times 10 or 100. And 10 to the third power would be 10 times 10 times 10, 100 times 10, or 1,000. Right, so common knowledge there. How this relates to logarithms is, since a logarithm really means exponent, this gives us another way to write this down that's helpful sometimes. So for example, this statement I can rewrite as log base 10 of 10. And so the two 10s I have here are this 10 right here is my base, right? And I wrote that base right here. So that's the base 10. And then this green 10 over here is the answer to that 10 to the first power. And then that 1 right there just ends up on the other side. And so I'll explain that a little more carefully for the next one. So I'm just going to rewrite this exponent statement as a logarithm statement and then emphasize that a logarithm is an exponent. So next statement says log base 10. Why base 10? Because the base over here is 10, right? And then besides the base, the logarithm needs something to look at. And we show it over here, the 100. And this says, what power of 10 gives you 100? And we would say, well, the second power of 10 gives you 100. So like if I speak out what this part means here, what this says right here is what power of 10 is 100. And we can say, hey, it's the second power, 2. Right, 2 is the exponent that gives us 100. So again, my point here is a logarithm is an exponent. The exponent is 2. Let's rewrite this one right here. So this one right here would be written as log base 10 of 1,000. And the interpretation of this is 10 to what power gives us 1,000? Well, it would be the third power. So that's the relationship between an exponent and a log. A log is the exponent. Now, because our number system is based on 10, we use 10s all the time in math and science. A lot of times this will be abbreviated. So on a calculator, it would just be log of 1,000 is 3. So if you see no base down here, it's assumed to be 10. So if no base is written, then assume it's 10. And then get your calculator out. Let's test this on a calculator. See it work in action. So I'm going to use, I'll use my Desmos calculator. Oops, wrong button. So Desmos, let's see, they don't have it on the main screen. I think we have to go over to the, on this version of Desmos, I have to go over to function, and then there's LOG. So if I say, okay, log 1000, if there's no base under the log, you assume it's 10. So this says 10 to what power is 1000? And the calculator says, hey, the third power of 10. Right? Let's bring up the Google calculator. Let's see who just joined our session. Maribel, welcome. Glad you could join us. All right, so my Google calculator has a log button right here, and I can ask it the same thing. Since there's no base written, we assume it's base 10. So if we say log of 1000, that says 10 to what power is 1000, and the calculator should say 3. 1000 is the third power of 10. So why bother rewriting these? What's wrong with just leaving it this way? And here is the brilliant idea someone came up with about the idea of rewording this in these following equations. So I know 10 to the third power is 1000. I know 10 to the second power is 100. So now I'm wondering, well, like, what about in between? What power of 10 is going to give me 200, for example? Well, it's got to be bigger than the power 2, because 10 squared is 100. 10 to the second power is 100. But the power has to be smaller than 3, because 10 to the third power is 1000. Now we can start guessing at that. You know, maybe it's 10 to the power 2.1 or 2.2. But we could spend a lot of time guessing. And like if somebody said, hey, I need you accurate to 3 decimal places, that I don't want to guess that much. So the trick of logarithms is to say, well, since a logarithm is an exponent, we can just rewrite this as log base 10 of 200 is the power we want. And on a calculator, the base 10 is just not written. So on a calculator, we would just say, hey, what's the log of 200? And what that'll give us is the power we need to get 200 as the answer. So let's give that a try. So what power of 10 gives us 200 on a calculator is just, hey, what's the log of 200? Because a logarithm is an exponent. So this will tell us what exponent to use. And it says it's about 2.3-ish, okay? So let's see, let's grab a whole bunch of those decimals. Let's grab all of them. I'm gonna copy, and I'm gonna clear this. And I'm gonna say, hey, let's take 10 and raise it to the power everything I just copied. Will it paste it in there for me? It won't do it. I gotta type it. 2.301029995566. Man, it's got a lot of them. I'm tired of typing. That's good enough. And it says that's pretty darn close to 200. So if you round that number anywhere, like if we just called it 2.3, 10 raised to the power 2.3, we just get kind of close to 200. Not as close as we were before. So the more decimals you include from the calculator, the closer you get to the target. So what do logarithms do? They find exponents. That's what they do. So we're just going to apply that idea to some other problems we were looking at. Like we were looking at population growth, we were looking at car depreciation, we were looking at compound interest. And before, we were just able to like pick a time and find out what the future amount was. Now, we can actually target a future amount and tell you what time it happens. So that's why I was calling this lesson Finding Time, because it was going to allow us to predict when we're going to get a certain amount of money with compound interest, or when a car will depreciate to a certain amount, and so on. All right, but we need to play with logarithms just a little bit more to get used to them. Some other powers of 10 that we've seen before. Reminder. So color 10 squared. Just pick on 10 for a minute. Is 100, and 10 to the first power is 10. It's important to remember that something to the 0 power is 1. And a negative exponent, you hopefully remember this from last quarter, means flip the base. So that would be 1/10. And if I had 10 to the power -2, the negative flips it and the 2 squares it. So that would be 1/100th. So a negative exponent doesn't mean you have a negative answer, it just means flip the base. So that's important. Review. Negative exponent means flip the base. And I could also write these in decimal form, like 1/10, 1/100th, like that. So then if I ask the calculator, hey, what is the log of 1/100th? What that really says is 10 to what power is 1/100th? That's the interpretation of what I wrote up there. And the answer should be -2, because I just did it backwards over there. So let's check that on a calculator. So we need to be good at using the log button on our calculator. So clear log of 1/100th, 0.01 is -2. So again, the log button here tells us what power of 10 some number is. And that given number is whatever we plug into the parentheses here. So it finds powers for us, and sometimes we need to know powers. So a more complicated example we'll come back to in just a minute is think about the car depreciation. We had this $26,000 car, and it was depreciating at 15% per year, which means our base here was 1 minus 0.15, 15%, raised to the power of time. Now we cleaned that up. 1 minus 0.15 was 0.85. All right, so remember this from lesson 4.2. So this is the formula for the car depreciation. So we said the amount the car is worth after t years was this equation. And we could do things like plug in t equals 1 and t equals 2 and t equals 10, but what we haven't been able to do yet is easily answer a question like, when will the car be worth $10,000? So we could guess and check by just plugging in a bunch of different numbers for t until we get close enough, but we don't want to have to do that. So it turns out we can get that power by using logarithms. So I'm going to come back to this one. It's a little more complicated. That's toward the end of the lesson. Let's do a simpler one. So suppose I had something like 10 to the power t was equal to 1500. And I want to solve for the t. Two ways to look at that. One way is the way I just said it, just rewrite it as a logarithm. So I want to know the exponent, and a logarithm is an exponent. Okay, so the log will eventually get it. The base 10 is the base of the log, which we don't have to write on a calculator, which means the 1500 has to go here. So on a calculator, if I just type, hey, what's the log of 1500? It's going to tell me what t is. So I just want to do that and check it. Log of 1500. It says it's the power 3.17. Let's suppose we went 3 decimal places, 3.176. So I just want to check that. What is 10 to the power 3.176? And the calculator should say it's pretty close to 1500. Okay. Now I rounded, so I didn't get the exact answer. All right, so I need more decimal places to get closer, but I'm going to say that's good enough right there. So it looks like my value of t here is approximately 3.176. And I checked it and got close to 1500. Another way to work with logarithms is logarithms have a special trick. So this is a special property of logarithms. What they do is they turn powers into multiples. So the log of any base to the power, let's call it t, can also be written as t times the log of that base. So they bring the exponent outside of as a multiple. And you might wonder, well, who cares? Why do I need that? And the reason we need that is the base isn't always 10. If the base is 10, it's a super easy translation from the exponent to the logarithm. If the base isn't 10, it's a little trickier. And this allows us to do any base, not just 10. So super important rule, write this down. We're going to use it today, we're going to use it tomorrow, we're going to use it the next day, and the day after that, and the day after that, for the next couple weeks. This is like 2 important things today. This is one of them. That powers in a log, the power comes out as a multiple. The other big thing is just what does the word logarithm mean? And the word logarithm is an exponent. If you know those 2 things, then working with logs isn't that bad. All right, so let's use this power rule here. So this is called the power rule because it manipulates the power. So I should write that down. Log power rule. Super important. All right, suppose we have an equation like 3 times 2 to the power t is equal to 25. Let's make it easier, 21. And we want to solve for t here. Well, when we solve equations, we get rid of things like multiplication by dividing. So the first thing I would do here is get rid of that multiplication by dividing by 3. Fortunately, 21 divided by 3 is nice. That's just 7. On the other side, 3 divided by 3 is 1. 1 times 2t is just 2t. So now I have the base to the power equals 7. And until today, we had no way to solve for a power. To solve for a power, we use logs. So this is the big thing about today's lesson. So what I do is I write log on each side. And on the left side, I have a 2t. And on the right side, I have a 7. And so I just write log of the left side equals log of the right side. Let's see. Oops, what did I do there? Okay. So now I use the power rule. I can bring that power down, which helps me solve here. So I bring that power down here. So I get t times the log of 2 equals the log of 7. Now the log of 2 is just some number. So I'm not going to write this down. I'm just going to go to my calculator and just show you. If you take the log of 2, it's just some weird decimal, 0.3, blah, 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 blah. Okay? It's just some number. I have t times some number. To get t alone, we get rid of the multiplication by dividing. And that number happens to have a weird name. It's called log 2. And I have to divide that to the other side, log 2. Now here I have a number divided by itself, which is 1. 1 times t is just t. Now on the other side, it would be nice to cancel the word log, but it doesn't work that way. So we're just going to check that on the calculator. So on the calculator, I'm going to pretty much type what I see here. So in my Google calculator, I would just type log 2, close the parentheses, hit divide, and then type log 7. Or did I do that backwards? I think I typed it backwards. Yeah, 7 goes in the numerator. Sorry about that. Back up. Log 7, there we go, divided by log 2. So that's what I wrote on my paper. It's just the division symbol looks different. Hit enter. Calculator says it should be about 2.807. I'm going to write that down, and then I'm going to check. So this is about wavy equals 2.807. Now we can check it in the original equation in a second, Now, a common mistake I made when I first learned logs was like, why can't I just cancel the log here and say the answer is 7/2? Well, how many times does 2 go into 7? 2 goes into 7 3.5 times. 2.8 is not 3.5, right? So you can't just cancel the word log. The log and the 7 are stuck together. They're a team, they're inseparable. So here I could cancel because it was the same number 2. The log of 2 was about 0.3, that's the same number down here. So that canceled because these were identical. But these have different things here, so the logs don't cancel. You just gotta plug it into your calculator. On my Desmos calculator, what does that look like? Pretty similar, but Desmos has the fancy fraction button. So I would do my log of 7. To get there from the main keyboard, I had to go to function. If you have like a Casio or a TI scientific calculator, there should be a log button right near the numbers. And then here I'm going to divide, divide over there, and then I have to go back and get my log of 2. And I should get the exact same answer that the Google calculator gave me, 2.807 roughly. If you want more accuracy, just keep grabbing decimal places. But we need to check to see if this actually worked, because this was some crazy stuff. So the only way to really check this is to plug back into the original equation. My original equation, I'm just going to squeeze a little check down here. My original equation said 3 times 2 to some power needs to be 21. We think that power is 2.807 about. So we're just going to plug the 3 times 2 to the power, this being the power, in and see if we get about 21. So over here, 3 times 2 raised to the power 2.807. And notice my answer over here, 20.99. That's pretty close to 21. If you want to get closer, then throw in more decimals. So 80735, getting closer. 49, getting closer. 22, hey, it got closer. Okay. Do I really need that many decimals? No, I think that's good enough. Right there, 3 decimal places. There's only some rare cases where we need more than 3 decimal places. All right, questions on those beginning examples right there? Okay, so I'm going to go back and I'm going to try and do this harder one back here. So I'm going to try to do that car depreciation problem where we're going to find the time. So this was the car depreciation from the last section. And we have our rate of depreciation. We were losing 15% per year is what this started. And the initial value of the car was, hey, we bought it for $26,000. If you lose 15%, that means you keep 85%, right? So our 1 plus R, where R is a negative number. So just a reminder about where this came from again. We want to know when is it going to be 10,000. So all I do is I set my equation equal to 10,000. So I say, okay, take that 26,000 times 0.85 to the power of t and set it equal to 10,000 and then solve for t. And again, we could just keep guessing at t, but that's kind of painful. A spreadsheet makes it a little easier, but we're going to actually do the algebra. So kind of similar to other algebra we've done, if we have a multiplication going on, we get rid of it by dividing. So we have to divide those 6 sides by 26,000 here. On the left side, a number divided by itself is 1. So I just have the 0.85t left. The other side I can clean up a little bit. I could divide top and bottom by 1,000. So that would be 10 over 26. I could just plug it into the calculator, but the problem with that is that's going to give me a crazy decimal I'm going to have to round. So if I just did the 10 over 26 or 10,000, over 26,000, I'm going to get the same answer on the calculator. If I round in between getting a final answer, that could throw things off a bit much. So usually if I get a weird fraction to decimal thing, I just keep the fraction. I could simplify it more, but it's not a huge deal. So I'm just going to call this 10 over 26 for now. Now I'm stuck at that point where, okay, I have this power. How do I get the power down? And the trick is logarithms. So I just take the log of both sides. So I say, okay, let's take the log of 0.85t. And that's got to be equal to the log of 10 over 26. And you really should be using parentheses with logs. Sometimes the online system doesn't. Point of using the log is the power jumps out. So I'm going to rewrite that. So now I get t times the log of 0.85 equals the log of 10 over 26. And again, I thought 10 over 26 was cleaner than that big long decimal we got. So I'm going to stick with my fraction. Last step, or second to last, is to get rid of this multiplication because we're trying to solve for t here. So we're going to divide by that number called log of 0.85. And it is just a number. It's some decimal, but we're just going to call it log of 0.85. It's kind of like, you know, pi is 3.14. It's similar to that. Now, resist the urge to cancel the logs on the right. It's totally illegal. It just doesn't work, as I showed earlier. On the left side here, though, I have a number divided by itself, and a number divided by itself is always 1. 1 times t is just t. So now I just have to go to my calculator and say, what the heck is that? And we pretty much just type it as we see it there. So use my Google calculator. Come here, Google. There you go. So I had in the numerator the log of 10 over 26, and then I have to close the parentheses for the log before I divide by the other log. So you really got to make sure you get your parentheses right. And then log of 0.85 on the bottom. And if my work's correct, then it looks like 5, almost 6 years later, the car should be worth about 10,000. So we're going to check it. I'm going to go for 3 decimal places. So I'm going to call it 5.879 years. So rounding, so wavy equals 5.879. And this answer should mean the years till the car is worth 10,000. Why do I keep writing care? No. Perhaps I need another cup of coffee. No, I don't. I'm hyper enough already. So the only way to check it is to plug in that number into the original equation and see. And our original equation said the amount of the car some years in the future was always the starting amount, 26,000 times that 0.85% that we keep to whatever power we want. We think the power should be 5.879. So then we're just going to plug that into the calculator and see, is that really about 10,000? Because that was quite a bit of algebra we did there. Let's make sure. So on my calculator, 879, 26,000 times 0.85, oops, I missed my point, raised to the power 5.879. And my rounding is a little bit under the actual number because I left off a bunch of decimals. So this should be a little under 10,000 is my prediction. Nope, a little over. Did I round up? I don't know. How did I mess that up? I don't know. But anyway, that's pretty darn close to 10,000, within 62 cents, 63 cents. So good, nailed it. So now the hard part is just you practicing this, getting used to applying these logs to figure out what the power is. All right, let's look at the lesson and then troubleshoot in groups. And I know some of you already finished the lesson, so if you want to work on something else, let me know. And then I have 2 more problems I want to go over after we play with the lesson a little bit. All right, so the point here is we're using an idea called a logarithm to solve equations, and there's just a reminder about how to solve equations, like addition undoes subtraction, division undoes multiplication, and now we have this new idea that logarithms undo powers that are missing. And then here is just some use to getting power. So I'm gonna, if you didn't already start this right here, I'm just gonna go over a couple of examples. Remember, what does log mean? Log says, what's the power? If there's no base with the log, then that means the base must be 10. So this says 10 to what power is 1,000? Well, the power is definitely 3. So I can just put a 3 over here. 100 is what power of 10? Well, 100 is the second power of 10. So that's what I put here. And the log says, what's the power again? And I just say, hey, the power is 2. If I jump down to part E, 0.1 is really 1/10. 1/10 is 10 to the negative 1. So what power is that? The power is -1. So this part right here is just getting used to what I was trying to show you in the beginning, that log without the base written means base 10. And it just says, hey, what power of 10 gives you what's in the box here? And so we're going to write it as a power, and then we're just going to state the power. So for example, this next one is 10 raised to the first power, and the power is simply 1. So that's just getting used to log base 10 on the calculator. What does it tell us? It's a power of 10. Then down here, we get just some slightly more complicated ones, like the log of 100,000. Okay, what power of 10 is that? Well, there's 1, 2, 3, 4, 5 zeros, so that would be 10 to the 5th. So the answer there should be 5. If you're not sure, just plug this into your calculator. Right? Calculator has a log button. You can whip that out. This one, I'm going to break into my board to write about. So why that's the answer besides plug it into the calculator. So on that problem, I was given, what is the log of 1 over 1,000? And remember, if there's no base written, it's base 10. So basically what this green thing says is 10 to what power equals 1 over 10,000? Well, 1 over something means to the power -1. So I could say that this is the log of 1,000 to the power -1. Negative exponent means flip the base. Things that were in the numerator go to the denominator. Now I see 3 zeros there, so that means it's 10 to the 3rd, but because it was in the denominator, then 1 over 1,000 is really 10 to the -3. What power is that? Well, it's the power -3, so if I plug this into my calculator should say, hey, that's -3. So in other words, 10 to the power -3 is 1/1000th, or in decimal version, right, tenths, hundredths, thousandths. So just kind of playing around with what does it mean to be a logarithm. And it just tells us the power. So at first we're doing problems we can do without a calculator to gear up for problems we do with a calculator. So let's see. Oh yeah, these are, right. Yeah, so like 150 isn't a power of 10 that I'm familiar with. So that's one where I have to just plug it into the calculator and see what the calculator tells me. Following that, we've got some equations we're going to try and solve. So a relatively simple one, and then they get harder. So I'm going to put you guys into groups to work on this. And if there's anybody that's already finished this and wants to work on something else, please let me know right now before I open the rooms up. I don't hear anything, nothing in the chat.